Let's graph the vertex form of quadratics. So for today, we're going to graph the quadratics from vertex form and list all of the properties. So let's get ready by grabbing your notes, paper, and calculator. I'll ask you to sketch the graphs along the way and plot at least 5 points on each. So let's just start with some thinking. How is a quadratic equation different from a linear equation? Well, a quadratic equation is y equals x squared, whereas a linear equation is just y equals x. So the exponent has changed. How is a quadratic graph different from a linear graph? Hopefully we know that a quadratic graph is going to be a parabola and a linear graph will be a straight line. So visually they look different. Is a quadratic equation a function? The ones that we do this year are going to open up and down, so they will pass the vertical line test, so they are functions. And what is the name of the shape? It is a parabola. So let's start with what we know. What is the parent equation of a quadratic? That's going to be y equals x squared. So when we go back to the very beginning on how we plot this, we can start with the very basic table of values. So if I plug in -2 and I square it, I'm going to get 4. Plug in 1, I get 1. 0 squared is 0. And then 1 and 4. And you can see we have this symmetry pattern. So if I plot -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. So you should plot 5 actual points, put arrowheads on your graph, and that is the parent equation of a quadratic and the parent graph. So there it is in Desmos. And if you remember what vertex form is, that's really just using our transformations. So our vertex form is y equals a parentheses bx minus h whole thing squared plus k. Let's talk about what each piece does. So in front of the a, if that is negative, that's going to be reflected over x. Then a will determine the vertical. If the absolute value of a, because now we're ignoring the negative because that reflects it, is greater than 1, it's going to be vertically stretched, which means it's going to be skinnier. And if it is less than 1, and of course greater than 0, it's going to be vertically compressed, which is going to look like a fatter graph. The b is then going to do it horizontally. And it's going to be opposite of what we think. So the absolute value of b is greater than 1, it's going to be horizontally compressed. And if the absolute value of b is less than 1, it's going to be stretched. Oftentimes when we think about the shift, we just look at h, but this does have a b there, so we have to consider that. So the shift left and right is going to shift h divided by b. And then plus y is going to shift up and down. That's going to shift my y value. So you can pause it here and write this. It's a little neater. And then the last thing to note is that the vertex is h divided by b comma k. So that would be the point of our vertex. So here's an example, and I'm asking you, what is the vertex? Be careful, don't be too quick to look at the 6. We do have our b here. So we want to set this piece equal to 0. So that really means that x of my vertex is 3. So this is going to go 3 units to the right, and it's going to go up 7 units, and it's going to make my vertex be +3, +7. In this, I am asking you to describe the transformation. So using words, describe everything. Well, the negative sign, the 4, the 2, and the 3. So that means I have to describe 4 things that are happening. So the negative sign tells me it's going to be reflected over x. The 4 is vertically stretched. And we say that's by a factor of 4. X plus 2 means it's going to go left 2 units. and plus 3 at the end means it's going to go up 3 units. And that's how I would describe the transformation of this quadratic. Write the function f of x equals x squared that is reflected over x, vertically stretched by a factor of 6, and translated 3 units left to create g of x. So using that description, can you tell me what g of x will equal after transforming the original parent graph f of x? Well, if it's reflected over x, that means it's going to be negative out front. Vertically means that the 6 is not inside any parentheses, and it's vertically stretched by a factor of 6. Translated 3 units to the left. Well, that's going to be in my parentheses, so be careful. Don't put the 6 in, because then that would be the word horizontal. 3 units to the left doesn't mean x minus 3. It means x plus 3. Don't forget your square. Remember, we have to make it a quadratic. That's a common mistake. Students will forget to put the square there. And there is no shift up or down, so that would be my final function, g of x. When we're looking at properties of parabolas, I'm going to ask you, does it open up or down? What is the step pattern? What is the axis of symmetry? And that's going to be a line. What's the y-intercept? Be sure to write that as a point, x, y. What are the x-intercepts? Maybe there's 1, 2, maybe there's not any. What is the vertex, and is it a max or a min? What is the domain and range? And we're going to do that in interval notation, and then describing the end behaviors as we approach infinity. So here we have this example. How does it open? Well, I'm looking right before the 3, and that's positive, so this is going to open up. With the 3, that's going to vertically stretch it. So my normal step pattern is 1, 3, 5. That comes from my parent graph, which means when I graph this, not this one, but the parent graph, I'm at 0, 0, and then I'm up 1 to the right 1, and then I'm up 3 to the right 1, and then I am symmetrical, and then it would keep going up 5 and over 1. So that's the normal step pattern. Once you have a multiplier out in front, I'm going to now multiply this by 3, so my step pattern becomes 3, 9, 15, which then from 0, 0 would go up 3 over 1, up 9 over 1, and you can see we are really vertically stretching that one. So let me erase that so we can see our problem. And now we want to find our vertex. So in the parentheses, I have x minus 1, so that means I'm going to move to the right 1. Outside, I have minus 2, so that means negative 2, and that's my vertex. Because it opens up, that's going to be a minimum. It's down at the bottom. Axis of symmetry. So because this is going to end up being symmetrical about that vertex, it is a line equation. It's always an x equals, and it's x of the vertex. So this equation becomes x equals 1. So let's go ahead and put together what we have so far. So if I'm going to the right 1 and down 2, I have that as my vertex. I'm going to dot in my axis of symmetry. That's the line, x equals 1. I'm going to use my step pattern of 3. So I'm going to go up 3, 1, 2, 3, and to the right 1, and to the left 1, and then I would go up 9 more, and that's going to go way off. So I'm going to try to graph that like that. What is the y-intercept? Well, because I just graphed it, I can see that it's 1 here, so I'm going to write that as the point 0, positive 1. But if I look back at my equation, if I were to multiply out this parentheses, I would end up with a positive 1 at the end. Then I would distribute the 3. So I'd have 3 minus 2, which is 1. So it does make sense algebraically that my y-intercept is 1. As far as my x-intercepts, they would be crossing right here. I'm going to save that for a little bit because that's going to be in the next part once we start solving quadratics. The domain I can state, and I'm going to use interval notation for all real numbers. So that's going to be negative infinity to positive infinity. My range is my y of the vertex. So this is 1, negative 2, which means I'm down at negative 2 and including negative 2. So it's going to be a hard bracket, negative 2 to positive infinity. And for my end behaviors, they are both approaching positive infinity. And we'll write out those statements. As x approaches negative infinity, y approaches positive infinity, and the other one as well. So good job. You are using transformations and the step pattern to plot at least 5 points and then answering all of your properties.